So yeah, thanks for attending my talk. This is joint work with my student Linpeng Zhang, and I want to make a short disclaimer. Maybe I can answer your question in the end, even though it's quantitative stuff, but I will speak about non-quantitative stuff in the very end also, in case you hate quantitative stuff. Okay, I will first show you a small overview of what we're going to see. So I will first revisit classical weakest preconditions, then I will lift them to quantitative weakest pre something, and then I will present our main contribution, which is quantitative strongest post something. Then I will talk about liberal versus non-liberal predicate transformers, or in our case, quantity transformers, and even about strongest liberal postconditions, which Dijkstra and Scholten somehow forgot or didn't care about. And in the very end, I will have some thoughts about Hoare logic and incorrectness logic. Okay, so let's start with revisiting weakest preconditions, and I will make this by example of a weather forecast. So we want to forecast the weather of tomorrow in Auckland. And our model here is the states of the program are just snapshots of the entire state of the atmosphere. Let's say we could capture the entire state of the atmosphere, and a program is then a state transformer. It takes one atmosphere state and tells me the atmosphere state in 24 hours. And predicates are mappings from states to true or false. These describe sets of program states. Okay, now let's use this for a weather forecast using weakest preconditions. So we're asking what will it be warm tomorrow in Auckland? Currently it's not super warm, but let's see whether we can use this to check. So we have our programs which describe how the atmosphere evolves, and we have a predicate F, and F maps an atmosphere state to true if and only if the temperature in Auckland is above 25 degrees. This is nice and cozy and warm. And the question we then ask is, given the current atmosphere state, will it be warm in 24 hours? Here's a picture. I will now go, this is not nice for the people there, but I'll stay here. So here's a picture. We are currently in this state here, in state sigma, and we want to know F of tomorrow. So will it be warm tomorrow? And for this, we use a predicate transformer, and the predicate transforms this post condition F, the warmness or not warmness, into a precondition. And what is a precondition? It's again a predicate, and it maps an initial state to whether in the final state the post condition will be true or not. This is weakest preconditions. And as you may know, weakest preconditions reason backwards through a program, but what they actually make is a forecast. You can see here, because the precondition is a condition on an initial state, it forecasts into the future. Okay, this is all known. Let's see an example. So here's our predicate for warm, and X is the temperature in Auckland. And here are 3 weather models. This weather model just sets the temperature to 2 degrees, here 27 degrees here. This may be more realistic in times of climate change, just increases the temperature by 1 degree. Okay, let's do weakest preconditions here. Okay, here it's false because it's just 2 degrees, very cold. Next, in this weather model, it's true. And in this weather model, it is true if previously the temperature was above 24 degrees. Then later, it's above 25 degrees. So far, so good. But as indicated by this ugly looking brown color. This is not very nice, so we'll now go to quantitative reasoning. And quantitative reasoning is a bit more fine-grained. And what does that mean? Well, you could think, yeah, above 25 degrees, that is warm. Oh, this is maybe already hot for you. So we're doing now a more fine-grained weather forecast. Our model and states and all that stuff is the same, but now instead of predicates, we use quantities. And quantities map program states to real numbers, or plus or minus infinity, instead of just true or false. Okay, and now we can look how this quantitative weakest pre thing would work as a weather forecast. So instead of asking, will it be warm tomorrow, we'll just ask immediately for the temperature of tomorrow. Now, program is the same thing, but now instead of the predicate, we use the quantity F that maps the entire atmosphere state to Auckland's temperature. Okay, and now we ask, given the current atmosphere state, what will the temperature be in 24 hours? And here's again the picture. We are again here, and we want to know tomorrow's temperature. So F measured in the final state here. Yeah, and for this, we now use a quantity transformer. It transforms this post quantity into a pre-quantity, and the pre-quantity maps initial states to whatever measurement we get here in the final state. Okay, this is kind of known already. This was done by Cozen for probabilistic programs, and then later also by McIver and Morgan, further done for also probabilistic programs with non-determinism. Yeah, so now we'll see examples how this works. I mean, this is obvious. Now we're asking here for what's the temperature after setting x to 2. Yeah, it's 2. For 27, it's 27. And here, this is maybe more interesting. Here, it's x plus 1. So we're forecasting what x will be after incrementing x by 1. It will be the initial value of x plus 1. Okay, now let's see what would strongest postconditions be. And this is our main contribution now. And strongest postconditions are kind of dual to weakest preconditions. So we'll also just dualize the weakest pre thing here. Okay, so first of all, even what it is kind of dual. It's not a weather forecast, but this is now a weather backcast. So naturally, we're asking, what was yesterday's temperature in Auckland? So now we're given the current state of the atmosphere, but this must now be this state. Yeah? We are now here, and we're asking what was yesterday's temperature. So yeah, what was the temperature 24 hours ago? So we're taking the fiber of this state. So measuring F in the initial state. Now, there's a small problem because even for deterministic programs, we could have had multiple states that lead to the same final state. So we measure F in every one of them. And how do we now resolve this? Well, we choose the maximum over all these possible values. Okay, and this is now what SP does. It transforms a post-quantity a pre-quantity, these Fs, into a post-quantity, and the post-quantity maps a final state to whatever the maximum initial value was of that F before executing the program. Okay, let's see examples again, or just one example actually, the x plus 1 example, and we're asking for x. And this is the rule that we have. If you are familiar with the rules for strongest postconditions, then here this upside down S, this replaces the existential quantifier in strongest postconditions, but here it's a supremum. So we choose a supremum over all values V. These are the the initial values of x. So we have basically the same rule as for strongest post conditions, just with quantities. So this thing here, this is an indicator function of a predicate, and this maps to plus infinity if the predicate is true, and minus infinity if the predicate is false. And this here is a minimum. So this takes a minimum between either minus infinity and something or plus infinity and something. Okay, now these things tell us to replace x by this by this v. So we'll do that. We get this, and we can always choose v so that this is satisfied, namely by choosing v equals x minus 1. So we do this also. And yeah, we end up with the strongest post, the quantitative strongest post of this program. And this tells us, if we plug in a final state here, say 5, then this tells us, well, before executing x plus 1, x was 4. Okay, let's put another program here. After this one, x becomes x minus y, and I will just give you the results. So this is now x plus y minus 1. Okay, now our subtitle said that this is also a calculus for reasoning about the flow of quantitative information through a program. And I will show you how, in which way this is true now. Let's look at a concrete state. Say x is 16 and y is 3. And the quantity we want to see flowing is x. So at this point, x is 16. If we execute this increment of x, then now x is 17. And the quantity, if we plug 17 in here, we still have 16, of course. We execute this, so we subtract from 17 3, we get 14, and if we plug these numbers into this expression, we again get 16. So we see how the 16 flows through this program. And if x was something secret, and this program tried to scramble the secret x somehow, then we get here an expression from which we can recover the original value of x. Now I would, as I said, I would like to tell you something about liberal versus non-liberal predicate and quantity transformers. So for weakest pre, we saw that we have a program and a quantity, and we want to anticipate what the value of f is, and this picture we have already seen. But what happens if there is no value to anticipate? Because the program doesn't terminate. So if the program doesn't terminate, then weakest pre will assign to this situation minus infinity. This is like the Dijkstra thing where you can interpret minus infinity as false and plus infinity as true. And then, Dijkstra would also assign false to this situation. So we assign minus infinity. So for now weakest liberal pre, what happens there? Well, in this case, we deem non-termination okay. So we assign now just plus infinity. So far, this is kind of known. But now comes something which we have never seen before. So for strongest post, we have also seen what this does. It retrocipates what the value of f was before. But the question is now, what can go wrong here? How can we have a liberal version of this as well? And this is the case if tau, a final state that we plug in, is not reachable. So there's no initial state that could ever reach tau. This can happen, right? And in this case, strongest post would assign minus infinity, so false. And strongest liberal post would assign plus infinity. And also for technical reasons, we have to switch here to a minimum now. So yeah, in a nutshell, we can say that weakest pre is about whether initial states can reach something, and strongest post is about whether final states are reachable. And the liberal versions then say, okay, non-termination is okay, and for strongest post, they say unreachability is okay. Okay, let's also see examples for this strongest liberal post thing. So for a reversible assignment, we already saw that. So I'll just skip through this. So x becomes x minus 1. And yeah, increasing x by 1 is reversible, so there's nothing that cannot be reached here. But the rule looks like this. We have an infimum quantifier now. This in a Boolean setting, this would correspond to for all quantifier. Then here we have unequal, and here we have a max. But yeah, it simplifies to the same thing. But if we have an irreversible assignment, now things become more interesting. Now this would go to the indicator function of x being 2. So why does that make sense? If we plug in a final state where x is 2, it tells us the maximal possible value that x could have had before, but it's anything, right? Because we just deleted all information about x. So it's, yeah, plus infinity is the supremum over all these values. For SLP, we get x unequals to 2, and this also makes sense. If we plug in 2, it tells us the minimum possible value that we had before, now minus infinity. But if we plug in a state, let's say x is 3, then we get plus infinity, and this is the okay value that tells us, yeah, this was unreachable, but it's fine for me. Okay, there's another thing why we think this strongest liberal post makes a lot of sense. So classically, this is very well known that if G implies the weakest liberal precondition of F, this is the case if and only if the strongest postcondition of G implies F. And this is also what defines partial correctness Hort triples, by the way. Our quantity transformers satisfy a very similar thing, but the quantity G is smaller than WLP of F if and only if the strongest post of the quantity G is smaller than the quantity F. But more interestingly, Dijkstra tried this. Dijkstra tried replacing WLP with WP, and he could prove that this is not possible to retrieve something on the right-hand side here. But here we just put WP on the left-hand side, and then we do get a Galois connection between WP and SLP. So yeah, WP and SLP. So I think this shows how this strongest liberal post very nicely complements the work of Dijkstra. Okay, finally, my thoughts on Hoare logic and incorrectness logic through the lens of this strongest post and strongest liberal post. So yeah, I showed you this already, or told you this already. So sorry, I told you this. So for partial correctness, we can define a partial correctness Hort triple. This is valid if this implication holds, yeah, using WLP. And for total correctness, we can replace WLP with WP. Now, there's this new logic, which is not so new. I should have put the De Vries and Kutawas there. They found incorrectness logic under the name reverse Hoare logic 10 years earlier than O'Hearn, but O'Hearn has recently popularized this. Yeah, and these incorrectness triples, I can define that an incorrectness triple is valid if this implication holds using strongest post. And yeah, I would claim we can also do something like partial or liberal or whatever incorrectness triples by replacing SP with SLP. Yeah, so I think this is one logic that would be worth investigating. And yeah, finally, this is my last slide. Yeah, we have seen, sorry, here that here we had WP, WLP, now we have SP, SLP. We can also put the transformers on the other side of the implication. And we have 4 transformers, 2 sides, so we get 8 combinations in total. But the blue ones and the orange ones are connected if and only if via a Galois connection. Yeah? So we get, I would claim, 6 and not 700 fundamentally different Hoare logics. We have total correctness Hoare logic. We have incorrectness logic or reverse Hoare logic. Then we have partial correctness, which is the same as here. Then we have what we would call partial incorrectness logic. And then we have 2, which I believe are completely unknown and unexplored. And I think, so our speaker before, I think this is something like necessity, right? Of course, it's a different setting because you had also kind of object-oriented features, I would say, and interaction with an environment. We don't have any of that, but I would claim that this is something like a necessary precondition. Yeah, but as we can see, this corresponds also to something like a sufficient, strongest liberal postcondition. Yeah, this table is also in our paper if you want to look at it again. And yeah, that's it. Thank you for listening, and I'm happy to take any questions. That's
Hi, thank you for the nice talk. I have a question about the question marks.
Yeah.
So, do you have any intuition what this calculus could be, or if it would be useful, or just like a?
Of course, it's useful, but I don't know. No, I have no intuition. We have not investigated this, but. Yeah, we have looked at, I think, the partial incorrectness thing, and it was kind of a necessity thing. It was if I have the password or I need the password to access something. And if I don't have the password, then I'm sure that I cannot access whatever.
Maybe a quick follow-up then. Why don't you have any intuition on the question marks? Was there anything that was particularly difficult there?
Yeah, time.
Time. I gotcha.
Yeah, no, we just haven't done it yet.
Yeah.
No.
Well, thank you for the presentation. I was wondering about the intuition behind using negative infinity and infinity to represent bottom and top, and whether that's related to the supremum and infimum, replacing the 2 quantifiers. And I was wondering whether that means you can't generalize. Is it possible to generalize this system to other quantitative types like complex numbers or matrices or strings, or is it necessarily limited to real numbers?
I don't think it's necessarily limited to real numbers. I will give another talk on weighted weakest preconditions in 2 days to make a bit of advertisement. There we have lifted at least the WP and the WLP to semi-rings. We are also not the first people to look at more general quantities from a semi-ring. I don't know whether complex numbers form a semi-ring off the top of my head, but
They're a field, so yes.
Yeah, okay, good. Well, you need a little bit more. You need an order on the stuff. So I'm not sure. Does that answer your question?
Yes, it does. Thank you.
Cool. Thank you.
Are you sure you can express something like total incorrectness? Because incorrectness logic only can express finite traces. So what does it mean to be total incorrectness? Totally incorrect, I guess.
Yeah, I just called it total to make a distinction to partial. So, but you can just call it incorrectness logic, and the other thing, I don't know, liberal incorrectness logic. So,
Okay.
my understanding is, it's a bit technical, but the WPs are least fixed points, and SP can also be captured as a least fixed point. And here we're trying to under approximate a least fixed point, so we can kind of enumerate finite stuff from below to approach a least fixed point. For the liberal versions, I can show you. For the liberal versions, even for SP, we replace for SLP with the greatest fixed point. So we can approximate this stuff from above. And we can do invariant style reasoning for SLP and WP.
So it's more I guess it's more powerful than incorrectness logic in that case.
No, I think it's not more powerful because the incorrectness triple holds if and only if this implication holds. So I don't think this is more powerful.
Okay.
But maybe we can discuss this
Sure.
Offline.
So I'm curious if what differences you get. You have weakest pre, weakest liberal pre, strongest post. What differences does that correspond to in the rules that you have for reasoning about specific programs, right? So so which rules are different? Is there like a generic picture that you can say these and these rules are where the differences happen, and if you put that there, then you get strongest post. If you put that there, then you get this.
Yeah, that's I think a very good question. So, yeah, how we did this, we basically dualized everything that occurs here. We made the equals and unequals, the min a max, and the exists or supremum quantifier and infimum or for all quantifier. And yeah, in here, for the if then else, you also have to switch this and this, so the mins, and you also have to make the guards negated. And we flip for the loops, but this is a semantic definition, we flip from least fixed point to greatest fixed point. But yeah, that's a rather technical statement.
So there's no sort of deeper underlying insight about how this connects to the semantic definition of the transformers. Or?
Yeah, I think I currently have no deeper insight, but this would be very interesting. Yeah. Anyway, if anybody wants to talk about any of this and developing this further, I'm very happy to talk to you.
Okay, maybe a final question, if anyone. No, so I think you have a lot of time for questions already. So then let's wrap up and thank the speaker again.
Thank you.